Alrighty, last video here for this section on implicit differentiation. We will be doing practice the next class meeting on this process so that we can get better and better at it. Notice that as we do the implicit differentiation, we're also practicing the other rules like the product rule, the derivative of a polynomial, the derivative of an exponential. We're going to mix it up so that you can continue to practice those other shortcut rules as you do this new process. Example 4. Can you write an equation of the line tangent to the graph of x squared minus y cubed equals 0 through the point 1, 1? So what do we need to remember? Well, we need to remember that the equation of the line tangent to the graph always uses this setup. Actually, I'm going to use, instead of f prime, do you mind if I just use m for slope? Because this is the formula that you should have learned or should have talked about in Algebra 1. That this formula can help us find the line fairly quickly if we know the slope, an x coordinate, and a y coordinate. Well, we're in good shape. We have an x coordinate and a y coordinate. So I could start to make my equation by saying x minus my x coordinate plus the y coordinate that goes with that x coordinate. Now all I need is to figure out the slope. But the slope of the tangent line is the derivative. So we need to find dy dx at the point 1, 1. So step 1, take the derivative of each piece on the left side. Since we're subtracting, I can use the difference rule that says if you're subtracting two things, take the derivative of the first, take the derivative of the second, and then subtract the answers. And I'm going to take the derivative of the right side, the derivative of 0, again, just 0. The derivative of x squared, 2x, minus the derivative of y cubed with respect to x means I have to do 3y squared times dy dx. And I've now implicitly differentiated my equation. I go to step 2. Step 2 says leave everything that has a dy dx on one side and then move everything else to the right. Well, this term has dy dx in it. And I'm going to move the 2x to the other side, so I'm going to have to subtract it over. Oh, didn't mean to do that. dy over dx. I think my computer's lagging a little bit. All right, step 3. Step 3 says factor out a dy dx. Well, I don't really need to do step 3 because there's only one term that has a dy dx. So I don't need to factor it out. So we kind of did 2/3 in this step. And now step 4, divide by whatever you're multiplying by dy dx. So dy dx is whatever was on the right side divided by whatever you're multiplying times dy dx, which would be this. You can also write it as positive 2x over positive 3y squared. But this is the formula that's going to help us find the slope, this last piece that I need for my formula, for my equation of the tangent line. So now that I have my derivative, now I can say, oh, at the point 1 comma 1, which is what they're talking about, dy dx is 2 times my x value divided by 3 times my y value squared, and that's just 2/3. That is the slope of the tangent line at the point 1, 1. So I come back over here and I write it in as 2, let me erase this part, as 2/3. And right here, my good people, is the equation of the tangent line. What I'm claiming is if I graph this equation in this, I don't know, greenish olive color is going to be the line that's going to barely touch that curve at 1, 1. Should we see it? Should we confirm? I kind of feel like we should. So x squared minus y cubed equals 0. So let's graph that first. Let's see. Where'd it go? Uh-oh. Now it's blocked. Well, I don't think we're going to be able to do it, my good people. I am messing things up here. Let's see if this works. Mm-mm-mm. I can't access the. Oh no, I can't access the keyboard because it's under this. Oh no. Okay, well, I'll show it to you in a subsequent video. That's okay. Maybe you can do it. Maybe you can do it on your Desmos. Graph this and then graph the formula that we found, and you're going to find that it's barely going to touch this curve at this point. That's what we're finding. And then finally, example 5 here. Can you, consider the curve given by this equation. Show that dy dx equals this formula. I'm going to be upfront with you. This is a very popular free response part where they probably won't ask you to do an implicit differentiation on the multiple choice, but as part of a differential equation question on the free response, they might ask you to do this step and just show that the answer is this. How do we show it? By doing those 4 steps. So I'm going to do it quickly because I don't want to take a lot of time here. So we're going to take the derivative of the first term minus the derivative of the second term and set it equal to the derivative with respect to x of the other side. I noticed that I have to take the derivative and I have x's and y's together, so I have to use a product rule. The product rule says take the derivative of the first times the second plus take the derivative of the second, which is 2y times dy dx, times the first. All of this is from the first derivative. I'm sorry. All of this is from the derivative of the first term. Minus, I got to take the derivative of this. Once again, I have x's and y's, so I need to do a product rule. Take the derivative of the first times the second. Plus, take the derivative of the second, that's 1 dy dx, times the first, and that takes care of the second. And that's going to equal 0 because the derivative of a constant is just 0. Now, at this point, I'm going to try to take away the brackets. The first brackets I could take away with no issue. The second one I can take away if I make sure to subtract both terms. So I have to minus this term and I have to minus this term. Now I can take the brackets away because I basically subtracted both terms, which is what they were asking me to do. All right, step 2. Anything that has a dy dx stays on the left side. So this has a dy dx minus 1 dy dx x to the third. But everything that doesn't have a dy dx, we're going to move to the other side, including this y squared. So it's going to become negative y squared. And this minus 3x squared times y, which will become plus 3x squared times y. And then I can factor out a dy dx. So dy dx 2yx minus 1x to the third. And then over here, I told you that you can put this first and this second, or you can write them backwards. I'm going to write them backwards only because I'm sneaking a peek to the answer, and they have it written this way. And now if I divide both sides by whatever's inside the parentheses, I'll get my dy dx equation. And my dy dx equation is y squared all over whatever's inside the parentheses, which would be this. This is what I'm saying the derivative is. And if you compare it back to what they wanted me to show, you're going to see that it's the exact same thing. By the way, notice in their version, they put 2xy. In my version, I put 2yx. That would be correct. They wouldn't take points off, obviously, because it's the same thing. If I had left the top as negative y squared, plus 3x squared y, again, it would have been the same thing. The moral of the story is we are taking the derivative of something that is not explicitly written as y equals something, x equals something, t equals something, w equals something. It's a mishmash, I guess, of variables, but I can take the derivative implicitly and still get a derivative formula that'll find the slope of the tangent line, the instantaneous rate of change at any point, as long as I have the x and the y coordinate there.